The following is a production of the University of Minnesota.
So today we have with us Professor Mos Kaveh, and Professor Kaveh received his BS and PhD degrees from Purdue University in 1969 and 1974, respectively, and his master's degree from the University of California, Berkeley in 1970, all in electrical engineering. Professor Kaveh has been at the University of Minnesota since 1975, where he holds the Centennial Chair in Electrical and Computer Engineering. And from 1990 to May 2005, Professor Kaveh was the head of our department. He currently serves as the Associate Dean for Research and Planning for the University of Minnesota's College of Science and Engineering. Professor Kaveh's research and teaching are signal and image processing and a broad range of applications from biomedicine to sensing and wireless communication. Professor Kaveh is also the past president of the IEEE Signal Processing Society and a fellow of the IEEE and the AAAS, and recipient of several best papers and other professional awards, including the 2000 Society Award from the IEEE Signal Processing Society and a 2002 Purdue University Outstanding Electrical and Computer Engineer Award. Professor Kaveh, we're really honored to have you here. Thank you so much for your time.
Thank you very much for your very kind introduction. It's not very often that I teach a course and get an introduction. But anyway, the topic of this lecture is quite unusual for a course on wind energy. It has nothing to do really with the design of wind turbines, with the placement of wind turbines, and so on and so forth. But it is something that is very important. It is one of those issues that, as engineers, we develop a technology and then find out that, well, this technology has certain unintended consequences, things that we have to worry about. And in the case of wind turbines, there are a number of environmental concerns that have been raised over time, including noise pollution for people who live near wind turbines, effect on, for example, bats and so forth, birds and bats and so on. But these are not the things that I'm going to be talking about. But one of the concerns that has been raised since probably particularly since the mid-2000s and started in Europe, particularly the United Kingdom, and then has spread worldwide, is the effect that wind turbines have on radars, and on really critical radars for either civilian or military or other types of operations. And because of this issue, there are many wind turbine development projects that have been put on hold. And as I said, in particular in European countries where space is more limited, so you have to worry about proximity to radars in this case, and so on, but also in the US. And so what we're going to talk about in any kind of a wind turbine project, as you know, this course is an outcome of a major research project on wind turbines. And one of the issues we had to deal with is to look at this turbine interference problem and see if there are potential solutions that we could forward. And as part of that research, I had a couple of graduate students. Let's see, how do I show them here? How do you use pointers? Just use that. Okay. And as part of this project, we had some industrial partners. In this case, the industrial partner was Lockheed Martin. And the main technical person working with us at Lockheed Martin at the time was Dr. Bachman. So I'd like to acknowledge her contributions to some of what I'm going to present to you. And then I had two graduate students who worked on this project, Jim Zhang and Brian Perfetti. Both have finished their work on this project and moved on, but I'd like to obviously acknowledge their work on the topic as well. So what I'm going to do in the course of this lecture is essentially to give you a high-level overview of what the problem actually is and why we have to worry about radars and radar wind turbine interaction. But this is a very broad audience, right? And even in the electrical engineering audience, very few students really actually work on radar these days or get instruction in radar. So what we want to do is to at least get the elements of what a radar system is like, how radar signal processing works at a very high level, and the key parameters that describe how a radar system actually operates and what its limitations are. Because some of those limitations then are going to reflect themselves into why we have to worry about the interference from wind turbines. So we're going to do some overview of radar systems, look at very basic radar detection concepts, and following that, essentially look at some examples of turbine interference with radars and conclude with at least a little bit of the results that we've obtained. One of the things I should point out right up front is one of the major difficulties in universities in working on this project is that a lot of the radar-related interference problems on this topic, for example, are confidential and are not open to public information. And so we actually cannot access some of those data that either have to do with air traffic control, for example, or for more military applications. But one area where we have been able to obtain data, not easily, but it is possible to obtain, and therefore the results I will show you later are focused on these, is weather radar. Because this is a concern, interference from wind turbines is also a concern on weather Doppler radars, and we'll explain why, particularly for weather Doppler radars. So that's essentially the story. Feel free to stop me and ask questions as we move along, but otherwise, let's take a look at what the topic is about. So the question is, why do we want to worry about turbines and what they do to radars? If you think about wind turbines, I expect some of you or all of you have seen them, or at least by the end of this course, know dimensions of these turbines. These are really huge structures. They're very, very large structures, and they're not single structures. In particular, you often deal with wind farms where there are many of these spread over space. And what does a radar do? Well, radar operates on the basis of reflection from targets. So you have very large targets sitting spread out all over the place, and these are naturally going to scatter, reflect the radar signals. And what that very large return will do is either through actually the structure itself or through the strength of what is reflected, essentially mask some of the legitimate radar signals that are obtained, and or just plain cause confusion, because you could have a major turbine sitting here, the radar signal bounces off of it, goes the other direction, hits a hill or a building, and bounces back, and so this creates a very complex signal environment that could be very confusing to radars, both in creating false targets and also eliminating or masking real targets. So as I mentioned already, we're going to look at radar basics, the interference problem, and then sort of summarize some of the areas where people have been working on to mitigate this kind of an interference, both through physical design as well as through processing of the information, the signal processing, which is the kind of work that we have been engaged in. Let's take a look at some major radar sites. What's the best way to do this? Not move or move?
No, that's okay.
It's okay for the taping?
Yeah, I think they can capture your voice.
Okay. Well, the voice is captured. I didn't know how well the video is captured. But let's take a look at this map. This is the map of the United States. And if you take a look at it, it is full of major radar sites. And these radar sites, as are indicated, are a lot of them have to do with air surveillance, basically aircraft, both civilian and military. And then many others are for basically for weather information. So if you take a look at these are, you can look at these more carefully later, but there are different classes of these radars that have, many of them are legacy radars. They've been around for many, many years. They're mostly analog systems, and then there are the newer versions of them, so newer generations. So you find, for example, the red dot, which says ARSR Generation 1 and 2. Those are some of the earlier air route surveillance radars, and these cover something on the order of 200 to 300 miles in range. And the older ones are scattered. For example, if you look at the Minneapolis-St. Paul area, there we have right at the Minneapolis-St. Paul area, we have an XRAD. This is actually a weather radar. We're going to look at some XRAD images later on. And then there is another one, which is what is called TDWR, which is a terminal Doppler weather radar. So this is what you need very close to the airport to get both the aircraft bearing as well as good weather information as aircraft are descending to the airport. But if you get away from the, this is so small that it's very hard for me to point to, so I don't, is it possible to make this a larger display on here or not? Because I can't.
Max a little weird.
Can you make the slide bigger so that I can actually point to it?
Yeah, let me exit the show real quick and then mirror displays. Otherwise you can just drag it.
Yeah, it's a little bit better.
That help out?
Yeah, that's a little bit better. I don't know what happened to it now. Okay. That's okay. So if you go to this point in Minnesota, you see one of the reds, which is one of the, it's actually a second generation air route surveillance radar. It's in Tyler, Minnesota. And later I will show a test flight that has been done around the Tyler radar to see what happens if an aircraft goes close to it, how well it's tracked, and so on and so forth. So these are distributed. If you go around the periphery of the country along the borders, you see the diamond. Those are the fourth generation air route surveillance radars, and those have been placed in particular for in addition to general routing, but very important for monitoring low-lying aircraft coming into the borders. So they're very sensitive. So if you think about, and then of course the weather radars that are spread all over the place. So if you think about particularly these radars, let's say monitoring the borders, and you happen to be close to a wind turbine or a wind farm, and then an aircraft comes close and flies close to the wind turbine, as we'll see, it is possible that you could go through undetected. That is why there is so much worry, at least from a security point of view or for even normal routing point of view. Then as we'll see, the weather issues are other concerns. So I've already mentioned this. The concerns cover weather radars, air traffic control radars, long-range surveillance radars. These are over-the-horizon radars that are going many, many hundreds of miles, 1,000 miles, detecting various kinds of flying objects, if you wish. And again, they could have major problems from the interference. As more and more wind turbines are built on water, marine navigation radars are a concern. Recently, I was at a radar conference where there was a demonstration of from Copenhagen. So as Denmark, as you know, is a major, they have a lot of wind energy and wind farms out in the sea, not too far from the city, and you could sit with a radar at the Copenhagen airport and it would just completely get lit up by the turbines out of these. So you have to have a way of distinguishing those from the aircraft that are approaching, for example, the airport. So these are things that I've already talked about. There is for those of you who are interested in digging in more, I'm not going to spend any time on this slide. One of the characteristics of the radars, of course, has to do with the frequencies they operate on. And the frequencies they operate have impact resolution, impact the distance they can operate in, and many other effects. And so you can see that here along this column we have the frequencies described, and on the top, essentially the types of applications that these radars are used for and what frequencies they operate on: airborne warning, space surveillance, weather, so on and so forth. But many of the ones we worry about then typically range within the 2 to 4 gigahertz range. So for those of you who are aware of what level of frequency one operates at, that's the range that we operate. So 2,000 megahertz to 4,000 megahertz, those tend to be typical of the radars that we have to be concerned about. I mentioned earlier that weather radars are the ones that we're going to particularly focus on in this course as an example. And so let's just take a quick look. You've seen a lot of these types of figures with weather radars on television, but typically what you get out of a system is that there is scanning the radar itself. And let me go backwards again. So you have a map, and then the radar basically scans in range, and it scans in azimuth, circles around the whole 360 degrees, and the return signals are processed appropriately and then displayed. In this case, the severity of, for example, rainfall, as you can see in the rain and so on. So this is essentially the way these operate, and we'll look at these a bit more in terms of their operation. And severe weather warning is a very critical part of what Doppler weather radars are used for, tornadoes and whatnot. And you can imagine that if you have interference and confusion with things like turbines, that could be a major area of concern. I show you one of these pictures from the National Oceanic and Atmospheric Administration, where you can see on one side the display of a Doppler weather radar. These are actually storms. And on this other side, these are returns from wind turbines in this area. So, and this is part of the confusion. Now, one can, of course, say, well, we know if you're sitting at a particular radar site, we know where these turbines are. At least one should be able to obtain the locations, and maybe that can reduce the level of confusion. But there are all kinds of things that happen with atmospheric propagations, with the fact that if the weather, instead of being on this side, had been on this side, then it could have major areas of confusion, errors in the level of precipitation, the wind velocities, and so forth. So again, that would produce erroneous results and cause either false alarms or misses in terms of warnings. So that's the way the weather radars tend to operate. In the case of air traffic control, we have a different type of a setting. In the weather Doppler radar, as you say, what happens is that the antennas tend to scan rather slowly. First of all, they sample, and we'll look at a picture again. They sample along the elevation. So at this elevation, then the next elevation, the next elevation. That's how they do the sampling at different elevations. And then within each elevation, we have a slow rotation of the antenna. And with that slow elevation, there is enough time to obtain reasonably good Doppler information. As we'll see, you do need to have some dwell time over a particular location to be able to get good estimate of what the velocities are, what the frequency shifts are within that element. So they can do that. In the case of air traffic control radar, this is no longer a possibility because you have to really follow fast-moving objects that move around, and you have to track these. So the antennas rotate much faster. There isn't that much time actually to do a lot of processing within each one of the cells that you're measuring. But a typical air traffic control radar like this often has, particularly sitting close to the airport, has a regular radar. This is this big dish here that you see rotating. And this one sends signals bounce back, just a regular radar operation. But they also have a secondary radar. The secondary radar is an active system. It's not really a radar in that sense, in that it sends a signal, interrogates the transponder on the aircraft. So these have to be friendly aircraft, obviously, where they have their transponders turned on. And in that case, the aircraft identifies itself, sends a signal, gives perhaps its location, height, and so forth, particularly with GPS right now. So you have multiple pieces of information to operate. But if it turns out to be a non-friendly aircraft, then that's no longer true because they're not going to turn their transponders on. And so that can cause the usual problems with the regular radar operation as well. So each one of these radars has their own particular characteristics, how much dwell time you have on a piece of information, how much signal processing you can do, or if things are moving just too fast that you can't spend too much time processing, and so you have to have some other way of doing the analysis and mitigation if you want to mitigate things. So getting this broad overview of the systems that we have to worry about, now let's look at some simple block diagrams for some radar systems and then talk about how radar detection will work. A basic radar system is extremely simple in its structure. You basically need some way of generating a waveform that you want to transmit, so a waveform transmitter, and these could be very complex waveforms. For those of you who are electrical engineers in particular, we're not going to worry about those. So waveform design is actually a major area of radar development. So that's one. Then once you generate the waveform that you want to transmit, you essentially send it through a big amplifier, a power amplifier, because you have to send a high power signal. And this goes through what is called a duplexer, and which means that if you're using a single antenna, you transmit, it goes out, but this same system, this duplexer also manages to get the received signal and then push that back through the receiver. And then this comes through a radio frequency amplifier, and this is at high frequency. We were talking about operating at 2 to 4 gigahertz or higher for some radars. So it has to be brought down to a lower frequency. That's what the mixer is, just like your radio receiver. Your radio receiver receives a high frequency signal that is at the carrier frequency of the station you tune in. How many electrical engineers are in this room? Okay, So supposedly the electrical engineers will follow some of these things more, but even if you're not, you probably have played with radios, so you have a sense. But anyway, when you tune a receiver, you tune at the carrier frequency, at the high frequency that the signal is transmitted, and then at the receiver send, this is mixed with the same with high frequency, and you get the cosine multiplications, if you wish, and then you get the difference frequency. The high frequency goes away, you low pass filter it, so what is actually operated on is at a lower frequency, which is called the intermediate frequency, IF, goes through another amplifier, and then finally these are either sampled digitally or an analog processor, and we end up getting the signal processing that will finally move into the displays that we've seen. So that's essentially the nature of pretty much any communication system. So transmit from either, in the case of radar, the same system transmits and receives. In the case of communication system, somebody else transmits, you receive, but in all these cases, you do some mixing down to a lower frequency, which has the information. The carrier frequency by itself doesn't have any information. It's, 2 gigahertz cosine, for example. But what comes out of it during the demodulation, which is the mixer, has the information that you want to recover, and then you process and move on. I mentioned earlier that in many radars, for example, the Nextrat weather radars, the radar actually tilts up, so it samples both in elevation and then also turns around in azimuth. So when you see these beams, so these are basically representations of radar beam, that is coverage, so you get a lower elevation transmission, and then you step that to perhaps the next level of elevation, another degree goes up, and within each one of these you have a rotation. Well, when you're looking way up there, then chances are that there's no problem with interference from the ground, but when you're at the lower elevations, then there could be wind turbines, or it could be a lot of things. Could be buildings and hills and whatnot that also interfere with a signal, but wind turbines are certainly there. I mentioned the over the horizon radars for very long distance monitoring, and those, of course, go around the curvature of the Earth. In fact, they get bounced from the troposphere. They do atmospheric bending, bouncing, and go very, very long distances. So in those cases, while you're sending them like this, they could actually come over and hit a turbine area as well from a very long distance. So that's the way the probing is done. But since we're going to talk about Doppler frequency, it's critical in the case of having to worry about the interference from the turbines. We should really get a sense of how the Doppler frequency is obtained, for example, in a classical way. The way you get essentially the low frequency characteristics of the signal, if you want both phase and magnitude, if you're interested in both of them, is to essentially get, if you wish, a phasor representation of the signal. Okay, how do you get a phasor representation? You want both a cosine component and a sine component, essentially an orthogonal projection of the signal. And this is done by taking the received signal. So first, when the received signal comes in, the mixer that I showed you now is actually represented by a pair of mixers, one of which mixes with the cosine of the carrier frequency, the 2 gigahertz or 4 gigahertz or what have you. And the other one is mixed with the sine, because cosine and sine are 90 degrees out of phase. So they essentially are orthogonal representations of the signal that is received. And then you run this through low-pass filter, and you sample this. So when you do this, what is obtained is, if you wish, for every sample, is a pair of numbers. The one that comes out of the cosine branch of the detector is called the in phase with a cosine component, or I. And then the other one is in quadrature, which means 90 degrees out of phase because of the sine. And this gives you the IQ representation of the signal. So if you look at from a trigonometric point of view, if you have cosine of omega naught t plus phi, and then you multiply this by, as I've shown here, with a cosine and a sine, and then expand the product, cosine, cosine, and cosine, sine. One of them, the in-phase one, will give you a component proportional to cosine of the angle, phi. The other one, the quadrature component, will be proportional to the sine of the angle. So in essence, by doing this thing, we have a complex number, or a phasor, representing that particular sample. And eventually, if this thing now has a time-varying phase, means that there is a frequency shift, time-varying frequency shift from the carrier frequency, then these are going to be proportional to the cosine and sine of that time-varying frequency. So there will be a frequency component and a phase component that will come out of it, and those, as we'll see, are how you represent your Doppler frequency shifts. So we'll be talking about IQ, and that's all it means, is just do this pair of mixing. So once we have these basic definitions, the elements of, the basic elements of doing the radar, solving a radar problem, is that that we have to design waveforms and a processor so that it has selectivity both in range, it has it in range, in azimuth, in elevation, and also if we're doing Doppler processing in terms of Doppler or velocity. So all of those things are the things that we're going to be interested in generally. So and once we have those characteristics fixed and designed a system for that, we want to, first of all, often with a radar, the first thing is to detect a target. So you set your range, the particular range you want to explore, and the particular azimuth, the particular elevation, and then the next question is there something there or not? Okay, that's the most basic element of a radar problem, and we'll talk about that. That's pure radar detection. And if you do have sufficient time samples within each one of these range and azimuth resolution cells, then you want to do more processing, because now you have a waveform. Okay, you have a waveform, so you can analyze that waveform and get something about what this target is doing. Target signatures of various forms are used to detect, to analyze what kind of a target it may be. And the most basic one, of course, is the velocity, to if the target is moving, to find out what the velocity of that signal is, and that's through the Doppler frequency shift. So what is a Doppler frequency shift? We need to have a definition for this. It turns out if you go through the derivations of how, if you have a moving target, you transmit the signal towards a target, moving target coming in or going out from that direction, then there is a shift in the frequency of the signal that is returned. And that shift is represented by this FD, so Doppler frequency in hertz, and that is defined as 2 times the target speed, the velocity of the target, times the cosine of the angle between the transmitted signal and the direction of the motion of the target, divided by the wavelength of the signal. So, excuse me, clearly the higher the frequency of operation of the radar is, higher frequency means the wavelength is smaller. That means that there is a larger Doppler that is created for the same velocity. The higher the velocity, obviously, you're going to have a higher Doppler, and the more aligned the transmitted wave is with the direction of propagation of the target, the higher the Doppler is, because the cosine in that case in magnitude is largest. So if you have if a target is coming directly at the radar, and then you get based on this definition, a negative Doppler frequency shift, and if the target is going away, then you get the positive Doppler frequency shift. And of course, you're familiar with this, I'm sure, based on acoustics, because the same thing happens with acoustical signals. When something is coming towards you with some noise, with some frequency, or going away from you, you can see how that frequency changes. So how do then these Doppler radars operate? Well, first of all, if you want to have any kind of a range selectivity, you can operate like the most basic police radar that only is interested in the velocity. And in that case, you don't need the range selectivity, the most basic one. Most basic one just shoots a sine wave at your car, and that sine wave comes back with a Doppler shift, and it rings a bell or whatever. It shows a number that shows you're going over the speed limit. But in that case, it's only giving you the Doppler. Okay, it doesn't tell you where you are exactly. But if you want to know where the target is, then you need some kind of a range resolution as well. And then within that range resolution, you want to know the target. So in that case, the basic way of getting that range resolution is through what is known as pulse radar. Okay, not a continuous wave transmission, but a pulsed wave radar. And in this case, if you're doing Doppler processing, then you have a pulsed Doppler radar. So how does this operate? Essentially, let's say in this case, there is weather, there is the radar, as you can see, and you transmit the first pulse, and this first pulse goes out, gets reflected. Okay, then you transmit the second pulse. So the vertical axis, as you can see, is time. So the first pulse is transmitted, and then this is essentially range, which also means time, because you transmit, then you open your receiver, and then click, 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 sample it, or open what is known as a range gate. Open it up as much as a pulse width and see what comes through. And so very little comes through at the beginning of this transmission. If this shows, it doesn't want to show. Okay. So you can see you transmit signal, and there's very little for a while coming back, and then it hits, in this case, this weather target, and then you start getting returns as the pulse propagates through the weather, and then it's out of the weather system, and then, of course, not much comes, just noise. And now you transmit a second pulse. So there is a repetition of these pulses. We're going to talk about these pulse repetition rate or pulse repetition frequency is important in the design of these radars. And there is also a width to this pulse, which is very important, and as we'll see, is related to how good a resolution, range resolution you have for the signal. So that's it. You transmit, you wait, transmit, wait, and then and these are indicated pulse repetition time between the pulses, and then each one of these signals that is returned, we talked about IQ, is processed to get the in-phase and quadrature component, and this, for each one of these, gives you one complex sample, a cosine component and a sine component, and then you collect these as a time series, which is at the bottom here. So within each one of these range resolutions, as the radar is moving along very slowly, hopefully, so within each one of these range resolutions, you have multiple pulse returns that come in. You have several samples that then you can process to get your Doppler frequency, do spectrum analysis or what have you. Okay, so that's essentially the way these work. in basic. So now there are a number of things that we're going to need to further describe how well a radar may operate. I mean, basically some of the other parameters that describes the characteristics of a radar and its detection capabilities. Above here, I have summarized again some things that we've already seen broader in terms of frequencies and what types of applications these are used for, what kinds of radars. Radar depends on the kind of antenna you use. If you have a big antenna, what that means is you're going to have a beam that is very narrow. The larger in space the antenna is, the narrower the beam, appropriately designed, of course. So you have a big parabola, you get a narrow beam. So because of the narrow beam, you're going to have good selectivity, both perhaps in the vertical direction and horizontal direction, in the azimuth. Okay, that's one of the things. So the antenna gain is a definition that goes with how narrow the beam is, because if your gain is small, basically it says that this is a small antenna, it sends the waves all over the place. Okay, so essentially the signal that is transmitted gets spread throughout the space. The power essentially in a particular small area will not be so high. But if you have a large antenna with a high gain, then you have focusing, if you wish, of the energy of the transmitted signal. So that's one thing. The other one has to do with the target. Okay, so how well you concentrate your signal and how well you receive signal depends on that antenna's gain. But then you have to have a target that returns that signal. And radar cross-section, there is a definition. Radar cross-section will indicate it as sigma. This essentially represents how well a particular target returns the signal. So definition-wise is essentially the ratio of the scattered signal squared to the incident signal squared, if you want to look at it that way. And this depends on a lot of things. It depends on the shape of the target. It depends on the material of the target. And that's why there's so much effort spent into designing, for example, aircraft that have very low radar cross-section, stealth aircraft, right? If you have a stealth operation, then the design of the shape as well as the material causes that aircraft not to reflect so much of the radar. So radar cross-section is the other important element. And if we think about radar cross-section, then there are a lot of characterizations of radar cross-sections for different types of objects. And a number of them are listed here, for example, different aircraft, missiles, and so on, missiles. And I don't know, what is this, the shuttle? Yes, the space shuttle at the end here. But look at this. So the radar cross-section of a Boeing 747 is on the same order, can be on the same order as a wind turbine. So that tells you why the worry. The wind turbine has the possibility of really being big. Big meaning not only physically big, but looking big to a radar, and that's represented by the radar cross-section. Now, turbines, of course, like a lot of things that are dynamic, have highly variable cross-sections. So although the maximum cross-section, as I showed you, could be very big, well, it depends on where the blades are, how the blades are turned towards the radar. So the tilt, the yaw, all of these things have an effect on how much the cross-section varies. So if you had a radar sitting there and watching the returns from a single turbine even, what you find is that it changes. It changes over time, and so I've just diagrammed it here as a possibility. For example, you could get a very large return, the radar cross-section for the top blade, and then things go down, and then maybe a smaller return from the bottom blade, if you wish, and then again the top blade and the bottom. Something like this. Of course, here it looks fairly deterministic, but in a real system and with wind changing and all of these things, then this looks a lot more random, but generally it comes in these essentially periodic peaks. So if you're sitting there with a radar and the radar is not moving and watching this thing, this shows up as a flash. So if you just look at the radar screen, you get these sort of periodic flashes from the strength point of view. So that part of the issues with turbines, that you have these levels of variation as well that we have to worry about. So I was talking about designing the radar, and we wanted both range selectivity, velocity selectivity, and everything else, ideally. And so what is the most basic way we could come up with a signal like that? As I said, this is not a complex signal. It's a pretty simple one. This is just simple pulse radar. It turns out that these are the basic characteristics of how such selectivities work. The range selectivity or range resolution depends on the bandwidth of the signal that you transmit. Okay? Think about a single pulse, something that is narrow in time or space, depending on what your major is. Okay? Something that's very narrow. If you do a frequency analysis of that narrow signal in time or space, you will find that it's spread. Its Fourier transform, Fourier spectrum is spread over time, right? So as you widen that pulse, that signal in time or space, then the frequency extent becomes narrower and narrower. So there's this inverse dual relationship between frequency content and in time or space and in the Fourier domain, in the frequency domain. So when I say large bandwidth, you can get this in different ways with the complex waveforms. But the simplest one is, if you were sending simple pulses, is to make them narrow. Okay? And this makes sense. If you design your pulses to be very narrow, then if two targets are close to each other, these two pulses are narrow enough that when the returns come from the two pulses, they will be separated. So you see them as two distinct targets. But if they're wide, then at some point, as the targets get closer and closer, their returns will overlap, and then you can't detect them. So that's really to think about it in its most simple way. So range selectivity or range resolution is inversely proportional to the bandwidth, or it goes along with the length. The narrower the pulse that we transmit, the higher resolution we have, which means that you can detect two signals that are close to each other. The opposite is true in how closely you can actually separate Doppler frequencies. It turns out that, again, for any of you who've done any kind of Fourier analysis, if you have a short few samples of a signal and then you run it through an FFT, do some frequency analysis, you find that even if it's a single frequency signal, a short segment of a sine or cosine, and you do a Fourier transform, this thing is going to be spread in the frequency domain, right? And so you don't get that. If now you have two frequencies that are close to each other, these spreads in frequency are going to interfere with each other. You're not going to have as much selectivity or resolution in frequency. So to get better and better selectivity in frequency domain, you will need to have longer and longer measurement of the signal. Take your sine wave and just have many cycles of it so that you can get a very high accuracy in the representation of frequency. So because of that, Doppler resolution depends on observation time. And I'll explain why these are important for us from an interference point of view. So those two are that way. And then the azimuth and elevation resolution we've already talked about depend on the antenna beam width. And that means you need a high gain to get good resolution in that sense. So if you sort of try to put these in specific parameters, then for a pulsed radar with pulse width, this is a pulsed radar, which we had looked at before. This is what you transmit. So a narrow pulse at the carrier frequency of, let's say, 2 gigahertz, then you wait the pulse repetition time and then transmit another one, and so forth. So in this case, the pulse repetition rate is T0, as I've described it here, and the pulse duration is TP. So in that case, then the range resolution is going to be proportional to the TP. If you have a narrow pulse, TP is small, you multiply that by velocity of light, which is the propagation time, and that gives you essentially something that is approximately the resolution in range, that you can separate signals with each other. And, bandwidth is roughly 1 over TP. So you can talk about this C times TP, or if somebody tells you this is a 10 megahertz bandwidth radar, you just divide by the 10 megahertz, and that gives you the range resolution. But these are pulsed systems. So if you transmit a pulse, one pulse, and wait for the next one to return, well, it could be that another range twice that far has now come back from a previous 2 pulse. So what happens in any kind of a periodic transmission of pulses, you're going to have ambiguity in ranges. So this limits you how far you can go without being ambiguous. And that ambiguity basically is, I've given you there, is again velocity of propagation C times half of the pulse repetition. Why the half? Is because you have a round trip delay. So you transmit a signal, goes, bounces off, comes back. So it's the time that it takes between pulses before things become ambiguous is half of that time. So you'd have to do these designs and watch for them. And then finally, the Doppler frequency ambiguity happens, again, based on the pulse repetition period. It's proportional to 1 over T0. Because, again, if you know anything about Fourier analysis of periodic signaling, there is a repetition. If you have a repetitive signal, periodic signal, you end up getting repetition in frequency at 1 over the repetition period. So that's why you have that. So I mentioned these to you because somebody who is doing the design for a radar system has to worry about all of these things. They have to know what range of targets are they interested in, how much Doppler do they want to sort of analyze, and how much range resolution they want to have. And I have to put all of these together to actually design the appropriate signal. And to be able to manage all of them, because there are competing issues involved here. One is 1 over 1 and the other one proportional to the other. What is really used in fancier radars is much more complicated than this. So for example, you don't just transmit a single frequency pulse, but code it with some fancy code and so forth. That things are used now in cell phones, for example, which give you a lot more selectivity. But these are the basic features that describe the characteristics of the radar. And then finally, if you want to know, well, when you put all of these things together and you have a target with a certain cross-section, how does the power that is received go with some of these different parameters? And that is a classic thing that has been known as the radar equation. And the radar equation essentially characterizes the received signal in terms of the transmitted signal, the gain of the transmitted antenna. In this case, I've used the same antenna for transmit and receive, so the gain shows up twice. The wavelength, and this wavelength shows up here because the gain, radar gain, depends on the physical aperture, how big the antenna is, and inversely proportional to the square of the wavelength. It turns out because the smaller the wavelength is, the higher frequency you operate, you don't need as big an antenna. It's really the wavelength normalized size of the antenna that is important, not the actual physical antenna itself. And so it goes by this, and then it has a range squared dependence inversely. And this is critical because what it says is that because of the wave spreading out as you transmit it spherically, you end up getting the power that gets reduced very, very fast. I mean, going out and the same one coming back after scattering from a point target gets similarly reduced. So the signal actually goes down significantly. So now you transmit a big signal, a very small signal gets back, which you want to increase as much as possible by making your antenna narrow, increasing its gain and so forth. And then you have to have a way of having a detection of that small signal that is returned in the presence of receiver noise, because there's always noise. Even if you don't have other interfering systems bouncing off, you always, an electronic system will have noise. This is the thermal noise that will be present to make things difficult. So, having said this, and by the way, we'll have a break shortly, but let me sort of finish this line. The very basic radar detection problem then becomes actually a statistical question, because there is noise, which is random. The signal itself, the radar cross-section itself is usually random as well, but we're not going to take that part of it, complicate things too much. But let's say even if you have a fixed signal returned with this level S, this is always at the receiver added with receiver noise N, which is actually receiver thermal noise is Gaussian, has a Gaussian distribution, a normal distribution. And so if you have a target, what this says is that at a given range, if there is a target, what you will receive is some small signal plus the noise of the receiver, a single sample of it. Of course, you may operate on many samples. And if there is no target, then the received signal is just noise. Okay, this is what is known as a binary hypothesis testing problem. Under hypothesis 1, we have one model for the received signal. Under hypothesis, the null hypothesis, H0, we have the model that is just the noise. Okay, and because of this type of setting, then you want to design a receiver, a detector, that in some statistical way, some statistical best way, then gives you a good result and tells you there is a target. So what do? In the case of radar, by the way, this is done, of course, in communication as well. But in communication, the aim is different than radar. In radar, often what you want to do is to, for example, get the received signal finally, in its simplest way, compare it with a threshold, some level. And if it goes above that threshold, you say, okay, there was a target in this range, a range cell at this azimuth, at this elevation. If it's below the threshold, then you say there's nothing there. All right, so the critical thing for radar designer is that you don't have false alarms quite often, because in many radar applications, false alarm is a major problem. Because you can keep, let's say that level was positive, S is positive, you can keep reducing the threshold towards 0 so that you will, you'll have a better chance of saying there is a signal there. But what happens? As you keep reducing it, you have a chance for the noise also to go above that threshold and give you false targets. So in this case, you have to come up with a good statistical test, and the classical one in the case of radar is what is known as Nyman-Pearson test. And this simply says, okay, if R is greater than this threshold psi, then say there is a target. If it's less, we say there is no target. But how do you choose the threshold? The threshold is chosen so that you want the threshold to be such that you can that you have an acceptable level of false alarm. Because it turns out that one can prove statistically that for that kind of a design, this particular test will also give you, for something like a Gaussian model, Gaussian noise, will give you the maximum probability of correctly detecting. So it fixes that false alarm and gives you the best probability of detection. That's the guarantee. And again, you don't have to worry about this too much, but if any of you have had a communications course, for example, or certainly the junior level probability course in electrical engineering, these should be familiar with, because you can actually calculate or set up the form of the detection and false alarm probability under this model that I showed you. And all it means is you have to integrate over the appropriate region above the threshold of two different Gaussian densities. Because if there is a target, then we have a Gaussian probability density function with a positive mean. So there's a mean, it's R minus S squared. In this case, I've used unit variance. And if there is no target, then then this is a zero mean. So now you're integrating over a signal which is proportional to e to the minus r squared over 2 is the probability density function for a zero mean Gaussian. And then you integrate these. These are tabulated integrals. There's MATLAB for them and so forth. They show up in terms of what is known as the complementary error function. But these are well tabulated. One can calculate them. And so what you will get, why doesn't this show? Oops. Well, we have a problem here. This particular slide, for some reason, is not showing. What you will get is a curve as you change this value of S and plot the detection probability against the false alarm probability. What comes out are a sequence of curves as you change the value of S that are concave. They basically go like this, go from 0 to 1. And then the next one goes from 0 to 1. Faster, and then as S increases, it goes much faster from 0 to 1. So it will do what one would expect should happen, because it says that as you change your threshold, as you decrease your threshold, for example, you increase your false alarm probability, but you also increase your detection probability. So the question is, how fast does that happen? And if the signal to noise ratio is high, which means the signal that is returned, is large, your detection probability will increase much faster than the false alarm probability. So that's where you want to go. This receiver operating characteristic is a common way of representing a particular binary test. And of course, if you don't use a detector at all and just flip a coin, then what you will get is a straight line that goes from this corner to this corner, which means you always have equal chance of being wrong or right. You don't want that. Obviously, you want to be as far away, pushed towards this left-hand upper corner as possible. So it's always monotonically increasing. It shows something like that. I wonder if this is a compatibility problem between a Macintosh and, I don't know. But yes. It's the signal. It's the signal level, the way we had in this model. So, whoops. The original model. So your received signal is let's say a DC value, just a constant, S plus N. and N is the noise level, representing the noise level. So in a way, it's more like RMS than it is the power itself in this case. It's the signal level or the amplitude. So, okay, let me, so this basically gives you the very basic elements of radar. And now what we're going to do next is to talk about another important source of interference in radars, and that is what is known as clutter, because that takes us to the wind turbine problem. So let's take, what do you like, 5? Yeah, let's take 5-7 minutes, and then we come back and essentially finish up with talking, becoming more specific to the turbines. Okay, so let's go back to this figure that we had some difficulty with, and now you can see the curves. So these are simply plotting this pair of functions that I had derived here, the two complementary error functions, as the value of S is changed. So, excuse me. And for different values of the threshold, yeah, psi that shows here. So if you go, pardon me? There. So if you, for each one of those values of psi that you choose and a given S, so here in this case we have S equal to 1, then you get, I wish this would go away. Okay. We should forget about the mouse because, yeah, okay, because this thing shows up and I can't see the bottom. Okay. So as, okay, it shows up. All right. As value, so for a given S, then as you change the value of psi, the threshold, you get a particular false alarm based on those equations that we had, and a particular detection probability, and that gives you 1 point on the on this curve, for example, for S1, and you keep increasing it, and as you can see, as S value of S or the signal strength goes up, then these approach their saturation point of detection probability equal to 1 much faster. So in this case, you can have a detection probability equal to, let's say, 0.9 at a relatively small value of false alarm. So that was the... Okay, so up until now, at least this previous example that I showed you, the problem was receiver noise. So as if there's a target out there, you're trying to detect that target, and the only source of interference in the receiver is the thermal noise, the standard receiver noise, the Gaussian. But in the case of radar, this is not the only thing that we have to worry about. In fact, most of the time, it's not the thing that we have to worry about. What we have to worry about is what is known as radar clutter. And radar clutter is interfering signals that are returned from targets other than the one you want. Okay, so you have an aircraft, as is shown down here. I hate to touch this. I don't want to touch, but if you look at the figure at the bottom, the radar transmits a signal. Its target is the aircraft, but the signal also goes all over the place and bounces off, in this case, a wind turbine, or it could be, building, or again, a hill or something. and both of them come back perhaps at the same range gate. In that case, actually what comes back from the clutter could be much larger than the turbine, than the target, in this case the aircraft, and that could be a major problem. So clutter is a major limiting factor in radar operation, and a lot of work goes on in designing processors that essentially deal with clutter. One of the things that is important to notice is that whereas in the case of receiver noise, you can increase your signal level, what you transmit, and that's fine. So more signal comes back, the noise is the same, you do better. But in the case of clutter, that does not help, because you transmit a stronger signal, well, stronger signal gets returned from the clutter as well. So signal level does not solve the problem. It has to be some other way, some other features that are used. One of the radar detection methods for dealing with clutter is to design a processor that gives you a constant false alarm no matter what the clutter happens to be. So if you know the clutter statistics, if you know the clutter parameters, you can actually design a system, a processor that will give you this kind of a constant false alarm, and give you whatever the best detection probability you can get. But quite often you don't know what the clutter situation is, and in that case, what is done quite often is that you look in surrounding cells of where the target is. You look, meaning the radar looks. Okay, tries to collect some statistics, some models about what is happening in the neighborhood, neighboring cells, resolution cells of where the target might be. Based on the information that it obtains from those, usually a statistical model, then it sets its detection threshold so that the false alarm is appropriate for that type of a detector. I just mentioned this because it's a very important, again, part of dealing with false alarms based on clutter issues for radar. But one of the at least most straightforward ways of dealing with clutter, if you have stationary clutters or clutters with different velocities, to somehow operate based on filters that will get rid of one of those signals that are returned. So if you have a stationary process, a stationary target, ground, or a building, and you have an aircraft or a car that is moving, well, the stationary target will have zero velocity, right? Zero Doppler. And whereas the moving target has a higher Doppler frequency. So you want to have some kind of a processor that actually discriminates between these two, does the appropriate filtering. And this is very common in for example, radars that handle aircraft. It is what is known as a moving target indicator, MTI. So a moving target indicator basically separates moving targets from clutters, from stationary targets that are in its vicinity. So take a look at this. This is an example of a very simple moving target indicator. The radar transmits a signal here. The same signal is bounced off the building, which is sitting there. It's stationary. It comes through, so this is the same one that we've looked at before. You transmit the signal. It comes through a duplexer. You mix. And then this is a very simple processor. You take the signal after the mixing down and sample it and run it through this very, very simple filter, which is you take this sample, delay it by one pulse period, okay, and take the same signal and subtract it from that. Now imagine what happens, right? If this signal is not moving, you get essentially a signal between two consecutive pulses, right? And then you subtract them, it eliminates or removes most of the one that hasn't changed. Whereas the one that has moved, the one that has a difference in characteristic will pass through. In fact, if you happen to do a frequency characterization of this filter, it turns out to be a very simple high-pass filter. So it basically nulls out, gets rid of signals that are at DC, around zero frequency, and lets through signals that are outside of that. And this is done very commonly, say, even with weather radar and so on. Not quite that way, but if it weren't for things like this, it would be impossible to operate around an airport, for example. So this is an example of a made-up display where there are multiple targets. There are targets here, here, and there are a bunch of targets down here. But this is an area within this range and azimuths where there is a lot of interference from stationary targets. And then once you go through a moving target indicator processor, it gets rid of this DC interference essentially, and the hidden targets show up. So this is very important. So we'll see in a moment why this is important for us to know as we move to a wind turbine. So let's take a wind turbine. Right? This is large. The rotor height is, in this case, around 110 meters. The blades could be about 60 meters, each one of them, and so forth. So that at the highest point, the blade is at 170 meters. There is some rotation, in this case, 12 RPM, for example. And what this means is that the tip speed, the linear speed, as this thing is rotating, could be as high, in this particular case, is roughly about 75 meters per second. It's over 200 kilometers per second, for example, in this particular sense. Okay, so if you're operating with 2 gigahertz radar, at its maximum, this moving rotor will generate a Doppler frequency that its maximum is roughly about 1 kilohertz. Okay, so this is the beginning of the problem with turbines, because although this large support structure is stationary, and so one could say, well, just use an MTI, moving target indicator, and that would remove this stationary target. This part is not. This part actually generates significant Doppler shift, and the Doppler shift can be as high as, depending on radar operating frequency and so on, certainly as high as some turbulent weather phenomena that one gets, and aircraft, particularly as they are approaching airports and so forth. There's something more complicated, though, in the case of the Doppler situation with turbines. So remember that the speed when you're rotating, the speed at the tip of the turbine is much higher than when you're close to the to the center. I mean, speed for this rotation scales with the radius. Okay, so you have this part of the turbine that generates very high speed, high Doppler, and this part, medium Doppler, this part, small Doppler. So what we have now is a target that not only is generating potentially high Doppler, but it's actually Doppler is spread. It's splashed all over the frequencies. So this is the biggest problem, because now even if you have an aircraft or a weather phenomena or something that occupies a narrow frequency range that you could separate from this part, well, there is this part also that then generates the kind of Doppler that interferes with the signal. So this complexity, it's highly variable over time. As I said, as the blades themselves move, wind direction moves, all these types of things, but also because it's an extended target with a distributed Doppler signature, so its interference is spread over the Doppler domain. Okay, I've already mentioned a lot of these, so I'm not going to spend any time on it, but it really summarizes the reason why the turbine effects can be serious and hard to mitigate based on Doppler processing, because they're variable, they're broad in Doppler. The scattering from different parts of the blades are different, and they can also mask because of the large structure, and then you have multiple ones of these. They can mask the targets that are in some ways behind the turbines. So you have to worry about all of those. I'm going to concentrate on the weather radar situation, as I said, because these are the ones in particular that we could get data from and do some Doppler processing. And they give you the possibility of actually doing better processing, because with weather radar, you have more time at every given range cell to actually obtain a larger signal and be able to do some fancy processing. The other ones are harder. The air traffic control, the antennas are whipping around so fast, there's very little dwell time on each target region, and so much harder to do signal processing on them. So this is an example of one of the many next generation radars that NOAA has deployed all over the country, and these are, by the way, constantly being updated. So I know that there's a new generation of these being put that, for those of you who know polarization, that operate actually with both vertical and horizontal polarization, that improves their ability to characterize weather. But at least up until this point, when I made this slide, there were 159 of these all through the country. So it's an active network of what we depend on for Doppler radar. This is one example that we use. The frequency is close to 3 gigahertz, 2.7 gigahertz. And the beam width, you remember we were talking about the gain of an antenna. In this case, the azimuth beam width for these radars is quite narrow. It's 1 degree. So high resolution pulsing. And these are some of the other characteristics. We were talking about pulse width for pulsed radar. In this case, the pulse width is 1.58 microseconds. The range resolution is about 250 meters. Every time you transmit one of these pulses, the receiver goes through many ranges that it covers. In this case, over 1,800 range gates, and the maximum range it covers is over 400 kilometers, as you can see, and so on. So these are some of the parameters we've already discussed, characterizing a pulse radar. If you take that signal, the IQ signal that comes out of a radar like this, and do a Fourier transform, essentially do a spectrum analysis on it, and look at the Doppler frequency, what you notice is what I was talking about, which is, in this case, if there is no turbine, for example, you would get a very large return at zero frequency. That's from stationary clutters, ground clutter, for example. That's a usual, ever-present source of interference. So you see this very large peak at zero frequency, which is zero Doppler, and then perhaps a weather phenomenon, which has this kind of characteristics, Doppler frequency, and the Doppler will obviously say something to the weather people about the velocity of the winds and so forth in the weather, and then eventually the precipitation and so forth. And then the rest of it is because of noise. I mean, that's essentially the way the description works. We've analyzed some of the data that we've had where there's been wind turbine interference in this kind of a radar. And so you can see, in this case, when there are wind turbines, again, the ground clutter is always there. So that's the turbine tower, as well as whatever comes from ground and whatnot, stationary. There is, in this case, there was some wind, and even in clear air, you do get Doppler because of dust and mites and everything in the air. So you get some return from the weather, and then you get this large spread, Doppler spread characteristic that is coming from the wind turbine blades, as you can see. That's the problem. In this case, they happen to be in different parts of the spectrum, so they're well separated. But if the wind were coming from a different direction, then it would be masked by the turbine. And this is an example where there's just ground clutter and there is no weather and it's just noise, essentially. If you look at the, if you could just focus the radar antenna in one direction towards the turbine and look at that over time, and analyze the signal over time, what you find is that, and analyze the spectrum of the signal over time, what you find is what I talked about. Now, in this case, in the spectral domain, is that as the turbine blade goes up, it spreads a big Doppler spread, smattering of a Doppler flash. You can see this is Doppler frequency, so it covers a large range of Doppler. It's not just one narrow frequency range. And it's likely that this one on this side, for the negative Doppler frequencies, is from the turbine blade that at its height, when it's standing up in this case. And then you get, when it's going on the other side, not as much of a return, so it's a smaller Doppler return. But this is a big problem. This is what we've been talking about, that you get this very large spread of Doppler that, again, could mask significantly. Now, if you're operating a real radar, you don't just sit there and look at one direction. The radar itself is rotating, the antenna is rotating, so you're scanning different areas, different ranges, and so forth. So it's not like you're sitting there seeing these flashes in the Doppler all the time, but within each one of the ranges, as you're analyzing them, you will get a broad Doppler spectrum. So in this case, we've plotted this in terms of velocity and then the azimuth. So in this case, the Doppler, the radar is scanning, going around the azimuth here, and this is the Doppler characteristics. And the weather, as you can see, has at different azimuth, has different velocity because the direction changes compared to the weather propagation. And these are stationary clutter, and then the rest, these are turbine Doppler spreads. But in this case, they're again separated in terms of their azimuth because the weather was here and the turbines were there. So you can see that you can separate them in azimuth, but again, once the weather moves over here, then they would be interfering with each other. These are some examples, again, of weather radar from NOAA. I mean, if you go through a NOAA website, you'll get a lot of these examples where, for this particular one, is someplace in New York, and they're showing the return from the weather turbines, from the wind farm. As you can see, significant, so confusing a lot of the other information. This is a close-up where the majority of the turbines are, just to show that there are problems. This is a case I mentioned to you, I showed you where Tyler, Minnesota has a second-generation air routes surveillance radar for aircraft. And it's an area, there have been a number of tests done because there are some wind farms near the Tyler radar. So there have been a number of tests done. In fact, one was done just this past summer. Unfortunately, we don't get the data, but somebody has it. MIT Lincoln Laboratory has it. And so what is shown here is how, in this particular case, this is a relatively small aircraft, as it was flying close to the turbines, that the radar lost track of the turbines. So of the aircraft. I don't know if you can see the different colors. So the track one, where it's green, is away from the turbines, and the radar tracks it. And in the case of the other track, then it loses its track. Again, one of the concerns. This is another from another report. I think it's the British report, and again a test where the track, the orange one, is the current plot, which is the track of the aircraft, but then when it gets to around the green ones, it loses the track. So the idea being that you have to come up with mitigation techniques that somehow manage these, either detect the turbines and mask them in some ways, reroute aircraft appropriately in the case of air traffic control, so that they wouldn't get into problems like this, or have some really clever processing techniques or multiple radars that will keep the tracks going. So let me just summarize then. I've already mentioned some of these things. Some of the recent attempts at trying to deal with, mitigate this interference approach. One is to come up with a stealth turbine. Of course, we have a lot of legacy turbines. Can't do anything about those. But can you come up with some kind of a stealth design, both material and design, so that the reflectivity is relatively low? As I said, the conference I was at a couple of months ago, the Japanese have some particular smaller turbines that are then covered with some kind of a shroud, and they were showing very low, relatively low reflectivity, but they're very different turbines, and their capacity are very different than these large ones that we have at this point. Some people have proposed sort of fancier schemes, multiple radars, what are known as holographic radars and so forth, that would eliminate and alleviate the problem of losing sight of the targets in some ways by covering the problem areas of the turbine. And as I mentioned before, possibly masking the areas, finding out where the returns are coming from the turbines, and then masking those, rerouting aircraft and so forth. But the bottom line is that whatever you have to do, you have to come up with a way. If you want to do it on legacy systems, then you have to come up with some kind of a processing that distinguishes based on some signatures, some characteristics between what is happening with the turbine and the legitimate targets, and take advantage of those. And they're not very easy because, as I said, the Doppler part is very problematical often, and the amount of time you have on a given range cell and velocity cell and so forth is relatively small. I'll show you one example of the data that we were operating with. In this case, this is some wind farm data, radar data that had been shared with us, and then also some weather data that was shared with us. The weather data by folks at University of Oklahoma, where there is a severe weather center research facility. And so in this case, as you can see, these are the range and azimuth, by the way. So this is a large area that is being looked at, range, azimuth, and the darker colors represent larger returns from the radar. The blue is essentially very little. Nothing is there. So this one is some kind of an active weather system that is going on by itself. In this case, it's superimposed on the returns from these wind farms in an area, so there is some overlap with the active weather. And we have an algorithm that we developed to automatically detect wind farms based on a number of signatures and so forth. And so using that algorithm, it has identified certain regions of in range and azimuth, which is now known as a clutter map for this particular situation. So it says essentially that in these areas you have problems potentially with a turbine. So one of the things that one may do in these cases is to go to those range azimuth cells with the problems and, for example, remove the spectral content, the biggest values of the spectral content in the frequency domain from the turbines, and then interpolate across the spectrum from the clean areas to somehow bring back the relatively undisturbed situation. So this is an example of one way of doing what I just mentioned to you. So this was the original weather data. These are a couple of ways of doing interpolation in range azimuth and Doppler once the detection was made, as I mentioned to you, and some level of sanity has been returned. I'm not showing you here, but then based on these, we've also estimated rainfalls and other characteristics of the weather after the mitigation, and those have been reasonably good, and these have been reported in conferences and so forth. Just another way of the critical thing is to use the differences in the characteristics of these signals. I have a few reports and a classic book by Skolnick. If any of you are interested in radar, you can certainly get a lot out of this book. It's actually a handbook, so it's many chapters on many different types of radar. Of course, it has nothing to in the case of turbines, because turbines are new. Even though this is a third edition, but nobody had really gotten to the turbine business. And then these interesting things I mentioned, NOAA has a lot published in this area on the web, so you can use those. So this is all I have for today, and I hope you got something out of it, whether you are interested in radars or not. But at least next time you're watching the weather report, you say, I know what that thing is. So, okay, thank you.